let's talk about an experiment. One that's so simple on the surface, but so incredibly profound, it basically broke our entire understanding of reality. This is a dive straight into the weird, wild heart of quantum mechanics, and it all kicks off with one question that's going to challenge everything you think you know. Okay, so let's just start with this question, right? It sounds like it's straight out of a movie. What if the very act of observing something actually changes what that something is? I know, it's a completely wild idea, but it's the key to the whole mystery we're about to unpack. So, where does it all start? With this, the famous double slit experiment. It's a ridiculously simple setup. You've just got a barrier with two little vertical slits cut into it. And behind that barrier, you have a screen that can detect whatever hits it.
I mean, that's literally it. The goal is just to fire something, anything, at this barrier and see what kind of pattern shows up on the screen behind it. Sounds easy, right? Well, you're about to see just how weird simple can get.
Okay, before we dive into the really weird stuff, we need to set a baseline. In our normal, everyday world, things are pretty straightforward. You've got particles, solid objects, and you've got waves. And they behave in very different, very predictable ways.
All right, first up, let's imagine we're firing particles. Think of them like tiny little marbles or grains of sand. We're just shooting them one by one toward the slits. Each grain is a solid little thing, so it has to go through either the left slit or the right one. It can't do both.
And the result? It's exactly what you'd expect. No surprise here at all. Over time, the grains of sand build up into two clear vertical stripes on the screen, right behind the two slits. Makes perfect sense. That's our particle pattern. Okay, so that's particles. Easy enough. But now what about waves? Imagine we're in a big tank of water and we send a ripple toward the barrier. Now, a wave doesn't have to choose a slit. It's spread out, so it actually goes through both slits at the exact same time. So let's just break this down for a second. Look at the comparison. Particles travel in a straight line, go through one slit or the other, and make two simple bands. But waves are totally different. When the new wavelets emerge from the two slits, they interfere with each other. The peaks and valleys add up and cancel out, creating this unique striped pattern. So, two clear outcomes, two bands for particles, an interference pattern for waves. Got it? Good. All right, you got all that? Because now we're going to shrink things way, way down. And this is where our everyday logic just completely falls apart. Welcome to the quantum realm. So the big question is, what happens when we fire an electron? One of the fundamental building blocks of matter. It's a tiny, solid thing. It's a particle, right? So if we shoot electrons one at a time, what pattern should we get? I mean, common sense tells you, right? It's a particle. It should act like one of our little grains of sand. It goes through one slit or the other, and eventually we should see those two clean, distinct bands build up on the screen. But yeah, that's not what happens. Not even remotely close. Get ready for this. This is what actually happens, even firing them one by one so there's no chance they can bump into each other. The pattern that shows up is the interference pattern, the wave pattern. What? How is that even possible? Seriously, just stop and think about that for a second. We're sending one electron through at a time. The only way it can create that pattern is if the electron goes through both slits simultaneously and literally interferes with itself. A single particle is in two places at once. It's just mind-bending. And if you think that's weird, well, it gets even crazier. The scientists who first saw this were totally baffled, just like we are. So they decided, okay, let's try and catch it in the act. Let's watch. So they came up with a simple idea. Hey, if the electron is going through both slits, let's just put a little detector right there at the slits to see which one it actually goes through. We'll find out for sure. So that's what they did. They put a detector right at the slits to peek at the electrons. They start firing them again one by one, and yeah, the detector works. It sees each electron go through either the left slit or the right one. But then they look at the pattern on the back screen, and the interference pattern, it's gone. It completely vanished. Get this, the very act of looking, of measuring which slit it went through, forced the electron to stop being a wave. It's as if the electron knew it was being watched, so it snapped into position and acted like a proper little particle, leaving just those two boring bands. Just by observing it, we changed the outcome. So what in the world is going on? This isn't just some strange party trick. This is a fundamental clue about how reality itself actually works. And all of this leads to this absolutely central, kind of mind-blowing concept in quantum mechanics called wave-particle duality. It means that tiny things like electrons aren't strictly particles and they aren't strictly waves. So think about it like this. It's not a wave or a particle. No, it's somehow both at the same time. Before we look, it exists as this wave of probability, just a cloud of possibilities. But the moment we observe it, we force it to, pick one and snap into reality as a particle in a single place. And look, why should you care about this? Because this one single experiment is the absolute cornerstone of all of quantum mechanics. This isn't just some philosophical debate. Understanding this weirdness is what makes technologies like your smartphone's transistors, lasers, and even quantum computing possible. It tells us the universe isn't some predictable clockwork machine. It's fuzzy. It's based on probabilities. And weirdly, it seems to depend on us, the observers. And that leaves us with this one final, really deep question to chew on. If the act of looking at something is what makes it real and solid, then what is an electron, or anything for that matter, when we're not looking? And honestly, that's a question physicists and philosophers are still arguing about to this very day.